Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Good
Good
afternoon.
afternoon. Good afternoon, all of you. So let us continue with our discussion without wasting any time. Last class we have discussed about electrode potentials in the D block series, that is in the 3D series especially. And let us comment on few more things on this particular electrode potential. Then we will go to the some important compounds of D block elements like potassium dichromate, potassium permanganate. What do you mean by this? Electrode potential of Cr plus 3 to Cr plus 2 is negative. What do you mean by this? If it is negative, what happens to delta G? Delta G is equals to minus NFE. Minus NFE means what? Of course, delta G naught is equals to minus NFE naught. E naught stands for the standard conditions and standard temperatures or standard conditions. Delta G naught, E naught, they are the change in Gibbs free energy and electrode potentials measured under standard conditions. Delta G is equals to minus NFE. Delta G comma E, delta G naught comma E naught. This refers to standard conditions. What is standard conditions? Standard temperature, standard pressure, all those things should be there. Standard conditions. So delta G naught is equals to minus NFE naught. What do you mean by this, students? Delta G naught is equals to minus NFE naught and E naught of Cr plus 3 to Cr plus 2 is negative. That means minus N is a positive quantity. F is a Faraday which is positive. E naught is a negative. E naught is negative. So what do you mean by this? Delta G naught is positive or negative? Negative of negative will be positive. Delta G naught positive means non-spontaneous or spontaneous?
Non-spontaneous.
Non-spontaneous. What do you mean by this? That means the chromium in the plus 3 state to plus 2 state, it is not undergoing spontaneously. That means that is Cr plus 3 will not convert to Cr plus 2 spontaneously. Why? Why? We have understood from
is more stable.
yeah, very good. Cr plus 3 is more stable. Why? This means Cr plus 3 is more stable because Cr plus 3 is not converting into Cr plus 2 spontaneously. That means Cr plus 3 is more stable. So what do you mean by this? Very good. Cr plus 3 has the electronic configuration of argon 4s0 3d3. So 3d3 means half filled T2G is there. Half filled T2G. Because of half filled T2G subshell, Cr plus 3 is more stable. Because Cr plus 3 is more stable, it will not convert to Cr plus 2 spontaneously. Because it is not spontaneous, delta G has to be positive. Because delta G is positive, can I say electrode potential has to be negative? I can go through from the Cr plus 3 state more stable to the negative electrode potential in the reverse way also. From the electrode potential of Cr plus 3 to Cr plus 2 negative, I can say Cr plus 3 is more stable. In the reverse way, I can also say Cr plus 3 is more stable due to half filled T2G. Because of that, it is more stable. Because it is more stable, it will not convert to Cr plus 2 spontaneously. If it is not converting into Cr plus 2 spontaneously, delta G naught should be positive because for non-spontaneous reaction, change in Gibbs free energy should be positive. If delta G naught is positive, electrode potential should be negative. Like that, we can comment. You look at this, students. E naught of Cu plus 2 to Cu is positive. What do you mean by this? Delta G naught is equals to minus NF E naught. E naught is positive means minus of positive into positive into positive. So therefore delta G naught is negative. Change in Gibbs free energy, standard change in Gibbs free energy is negative. So what happens to this? What do you mean by this? This means reaction is spontaneous. Reaction is spontaneous or change is spontaneous, which means Cu plus 2 can convert to Cu. Yes or no? Which means Cu plus 2 can convert to Cu. Right? Is that clear, students?
Yes, sir.
Yes.
Yes. Yes, very good. Then we have some table of electrode potentials. You don't need to remember the values of electrode potential. That is not possible. No one can remember all the values, and the examiner also do not expect us to remember all the values. But the information or the data is important. Comments. Need not memorize the table, but remember the comments. Titanium, like electrode potential of +3 to +2, +2 to 0. If you look at titanium, +3 oxidation state is more stable. For the each element, which oxidation states are more stable, you have to remember these. You can get this data from your electrode potentials also. For titanium, you don't remember these values. Values are not required, but the comments are important. So titanium +3 oxidation state is more stable. Vanadium +3, chromium +3. For manganese, iron, cobalt, you are going to have +2 states more stable. For nickel, you have +3 oxidation state does not exist. Yes or no? For nickel, +3 does not exist for nickel. Why? Because nickel is more stable in the +2 state. If you write the Na+2, you will be having D8 electronic configuration. The D8 electronic configuration will be having 6 electrons in the T2G and 2 electrons in the EG if you look at the complex structures. And it has no tendency to lose the electron, one more electron to get the +3 state. So +3 oxidation state does not exist for nickel. For copper also, +3 oxidation state does not exist for copper. 0 oxidation state is more stable. 0 oxidation state for copper is more stable because of 4s1 3d10. Because of 4s1 3d10 electronic configuration. For zinc also, we cannot have +3 oxidation state. Zinc exists in Zn+2 only. Copper, Cu+2, but 0 oxidation state is more stable. Nickel exists in +2 state only. Manganese, iron, cobalt, +2 oxidation state is more stable. Titanium, vanadium, chromium, +3 oxidation state is more stable. All of these you can understand based on electronic arrangements. And from the electronic arrangement, from the structures, from the ionization energies, from the sublimations, from the hydrations, you can calculate the electrode potentials. Because electrode potential is not a single entity. It is obtained from the result of enthalpy of atomization, sublimation, ionization energy 1, ionization energy 2, and your hydration enthalpies. So all of those have the effect in these values. So from these value we are commenting. So this is the right order. So titanium, vanadium, chromium, +3 state is more stable. Manganese, iron, cobalt, +2 state is more stable. Nickel, copper, and zinc. If you look carefully, nickel exists in +2 state only. Zinc also in +2 state only. Copper exists in 0, +1, +2 states. Out of all these, 0 oxidation state is more stable. All of you just note down this. The comments you can just note down and let me know if you're done. Can I proceed further, students?
Done, sir.
Done? Okay, fine. Why is Cr+2 reducing and Mn+3 oxidizing when both have D4 configurations? Write down this. Question. Why is Cr+2 reducing? Cr+2 has electronic configuration of argon 4s0, 3d4. Mn plus 3 has electronic configuration of manganese will have argon 4s2, manganese will have argon 4s2 3d5. Mn plus 3 means argon 4s0 3d4. Cr plus 2 is reducing. Cr plus 2 is reducing means what? What do you mean by reducing?
Tendency to gain electron.
It is acting as a reducing agent. That means Cr plus 2 is reducing something else, means by itself it will undergo oxidation or not?
Yes. Yes.
Yes or no? Something which is acting as if I am reducing something else, I should undergo oxidation within myself. The oxidation alone cannot happen. The reduction alone cannot happen. If one is undergoing oxidation, if one is undergoing a loss of electron, that lost electrons has to be gained by some other species. Yes or no? So Cr plus 2 is reducing means there should be some other species which is undergoing oxidation. Cr plus 2 is reducing means it is making something else reduce. So within itself it should undergo oxidation. Oxidation means it should lose the electron. So if it lose the electron, it forms Cr plus 3. So in Cr plus 2 you have D4. If it loses the electron, it forms D3. D3 means it has half filled T2G. Half filled T2G, because of that it is stable. For manganese, what you will have? Mn plus 3 is oxidizing. Oxidizing means it is oxidizing something else by undergoing reduction within itself. That means it is gaining an electron. If it gains an electron, it will get Mn plus 2. For manganese, plus 2 state is more stable because it has D5 half-filled electronic configuration. For chromium, D3 is more stable when compared to D5 because of this T2G half-filled configuration. T2G half-filled. For manganese, D5 is more stable because of half-filled. So that is why Cr plus 3, Cr plus 2 will be converting into Cr plus 3. So it is reducing. So Cr plus 2 to Cr plus 3, if you look at electrode potential, it is positive. Mn plus 3 to Mn plus 2, if you look at electrode potential, is positive. That means delta G in both the cases is negative. Reasons are these reasons. What are the reasons? Cr plus 2 is reducing because if it undergoes oxidation, it will get a D3 electronic configuration which is half-filled T2G cell. Mn plus 3 will undergo reduction because it is oxidizing something else. So if it gains an electron, it gets D5. So it is going to be half-filled. So because of these reasons, you can say Cr plus 2 acts as a reducing agent and Mn plus 3 acts as an oxidizing agent. Is that clear, students? For Cr plus 3 when compared to D5, D3 is more stable because of half-filled T2G. You may ask a question, sir, why can't manganese also undergo a loss of electron to get D3? So that again it will get half-filled T2G rod. For manganese, the most stable oxidation state is plus 2 states. For chromium, it is plus 3 states. Right? Okay, these are the different properties shown by D block elements. So then we'll be understanding about different other compounds or different compounds of your D block elements. In our course, we have only two compounds mainly: potassium dichromate and potassium permanganate. Potassium dichromate and potassium permanganate, these are in our syllabus, students. So we have to understand about their structures, about their properties in more detail. And K2Cr2O7, it is a very good oxidizing agent or reducing agent. K2Cr2O7.
Oxidizing.
Oxidizing.
In your organic chemistry, we are going to use this K2Cr2O7, KMnO4 very frequently. They are very strong oxidizing agents, right? So preparation, first you look at the preparation. Dichromates are generally prepared from chromate. Chromate is CrO4 minus, CrO4 2 minus, which in turn are obtained by the fusion of chromite ore. Chromite is FeCr2O4, that is Cr2O4 2 minus, with the sodium or potassium carbonate in the free access of air. So what they are trying to say, you are going to generate chromate CrO4 2 minus, CrO4 2 minus. From the chromates, you are generating dichromates, Cr2O7 2 minus. These are your dichromates. Dichromates are prepared from the conversion of chromates. And how these chromates are obtained? They are actually obtained from chromite ores. Chromite ore. So this is your chromite ore. Chromite ore of iron, FeCr2O4. FeCr2O4 dissociates to give Fe plus 2 and Cr2O4 minus 2. That is your chromite ore. Dichromates are generally prepared by chromate, which in turn is obtained by the fusion of chromite ore with sodium or potassium carbonate in the presence of air. So the reaction of sodium carbonate occurs as follows. The chromite ore reacts with Na2CO3 in the presence of oxygen to form chromate. Write down this, all of you. These you have to remember equations. The mechanisms of inorganic reactions are not required. Like you may ask a question, sir, how you can say this complex reaction is happening? How we are saying that FeCr2O4 in the presence of Na2CO3 and oxygen, it is converting into Na2CrO4. Then we have to look at the mechanistic approach, which is much more complex. That is not in your syllabus. The mechanisms of inorganic reactions, write down this point also. Mechanisms of inorganic changes. Mechanisms of inorganic reactions are out of our course. In organic chemistry, we will be discussing the mechanistic part, like how the change is happening, why it is happening, what are the different reasons. For inorganic chemistry, we can't look at the mechanistic approach. So chromite ore is converting into chromate, and this chromate is used to get your dichromate. How the chromate is used? Yellow solution of sodium chromate. Chromate means CrO4 2 minus. The chromate is yellow in color. Either you take the sodium chromate or potassium chromate, they are yellow in color. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid. That means in the presence of acid medium, the chromate ores are converting into dichromates. CrO4 2 minus plus H plus, it is converting into Cr2O7 2 minus. If you do the reverse, like if you add a basic medium, then the reverse can also happen. Cr2O7 2 minus can convert to CrO4 2 minus in the presence of OH minus. The chromates and dichromates are interconvertible if you change the pH of the solution. Write down this point, students. Yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromates. Dichromates are orange in color. If you take sodium dichromate or potassium dichromate, both are orange only. Sodium chromate or potassium chromate, both are yellow only. You may ask a question, sir, why you are saying sodium dichromate and potassium dichromate, both are orange, or why you are saying sodium chromate and potassium chromate, both are yellow? Because if you look at the structures, Na2Cr2O7, it will give 2 Na plus ions and Cr2O7 minus 2. Yes or no? The Cr2O7 minus 2 is responsible for the orange color. Whether you take Na2Cr2O7 or K2Cr2O7, you are having Na plus and K plus ions surrounding the dichromate ions. These dichromate ions are orange in color. These dichromate ions are orange in color. Write down this point, students. The yellow solution of sodium chromate is filtered and acidified with sulfuric acid to give a solution from which orange sodium dichromate can be crystallized. Now you will be getting a clarity, sir, how we are commenting on color. Can anyone say what is or why the color is shown by the D block elements or by complexes?
Ligand to metal charge transfer.
Very good. Ligand to metal charge transfer in this case. Yes or no? But in general, how the color can be explained? The color is due to DD transitions. Color of
Transfer of
complexes.
ion.
Yeah. Color of complexes generally is generally due to DD transition. DD transition. What do you mean by this DD transition?
Transfer of electrons from T2G to EG.
Very good. Transfer of electrons from the T2G to EG. So we have the 5 d orbitals which are not having degeneracy now. So in the T2G level, if we have an electron, that electron can go into the EG level. That electron, once it go into the EG level, is it stable? The electron, is it stable in the EG level or it's stable in the T2G level?
No, it will emit a radiation and then will come back to T2G.
Very good. It will emit a radiation and it will come back to T2G. So understand the scenario, students. You have a complex here. In this water bottle, I have a complex, imagine, and I am giving some radiation. This is the source. From the source, from the electromagnetic radiation, I am giving some energy, like it has some VIBGYOR of radiation, let us say. From this particular VIBGYOR of radiation, can I say every radiation will be emitted by the, will be absorbed by the electron, or only some part will be absorbed by the electron?
Some part.
Only some part, no. Which part will be absorbing? The energy difference, whatever you have, E, the delta E, this part will only be absorbed. So we are giving the source. From the source, we are getting the electromagnetic radiation. It has a lot of frequencies, lot of wavelengths are there. Out of all those wavelengths, only a single wavelength will be absorbed by the electron. Why? Because that single wavelength will be corresponding to the energy difference between the T2G levels and EG levels. Delta E has to be is equals to Hc by lambda. So this delta E, the energy difference between T2G and EG levels, that will correspond to Hc by lambda. So that should be corresponding to a specific wavelength lambda. Yes or no? So out of your VIBGYOR of radiation, only a specific wavelength lambda is absorbed by the electron. As it absorbed by the electron went to the higher energy level. That's fine, but what happened to the remaining radiation? Whatever the color I am seeing is not the color with which the electron go to the higher energy level. Whatever the color I am seeing is the complementary color. You imagine this situation clearly. I have a radiation like this. Yes or no? I have a radiation coming like this. Because of this radiation coming and hitting this particular complex, the electron went to the lower energy state to the higher energy state. The electron went from lower energy level to the higher energy level. But I am standing where? I am standing here. Okay. Source is somewhere there. From the source, we are getting the light. From the light or from the source, we are getting the electromagnetic radiation. That electromagnetic radiation is hit by the complex. Because it hit the complex, the electron from the complex went from lower state to higher state. But what I am seeing is the left out radiation. I am not seeing the color with which the electron has been excited. I am not seeing this lambda. What I mean to say is this lambda is equal to Hc by delta E. That is the wavelength chosen by the electron to go from T2G level to the EG level. But what I am seeing, the color of the complex is the complementary color, not the color which has been absorbed by the electron. Understand this point carefully. What this point means is, from the VIBGYOR, let us say electron in that particular complex absorbed your violet color. Violet, blue, green, yellow, orange, red. We do have indigo, but that is not having a greater region. So I have written B, B, G, Y, O, R. Let us say what I am saying now is violet color corresponds to a particular lambda. Every color corresponds to lambda. It will correspond to lambda. This lambda will correspond to a particular energy difference. Yes or no? Let us say the electron is now observing this violet color. If it absorbs this violet color, that means it has absorbed some wavelength. What I'm going to see, I'm not going to see the violet color. The complex for me looks like yellowish in color, because what I'm seeing is the left out radiation, not the radiation absorbed by the electron. Are you understanding this point?
Yes, sir.
All of you understood this point or not? The color of the complex, whatever I am seeing, is not equal to the color of that particular complex which has been absorbed. If the complex absorbs one color, I will see a different color. If a complex absorbs violet color, complex absorbing violet color means the electron in the complex absorbing violet color, then I am going to see the color of that complex as yellow, not violet. Understood now? So the color whatever I am seeing is not the color which has been absorbed, but the color which has been emitted out. That is what your color concept means. But for this whole scenario to occur, what should we have? For this whole scenario to occur, the electron should be there. At least one electron, one unpaired electron should be there. Yes or no? If whenever we have an unpaired electron, then only we are going to have a DD transition, then only we can show some electronic transition happened, then only we can have a color. Now look at Na2Cr2O7 or K2Cr2O7, where you have dichromate ions, Cr2O7 2 minus ions. Try to calculate the oxidation state of chromium here. 2 chromiums are there, 2 into X. 7 oxygens. Oxygen is in which state? 7 into minus 2. Yes or no? 2 into X plus 7 into minus 2, that is equals to minus 2, total charge of this ion. So what is the oxidation state of chromium here? Chromium has an oxidation state of 2x is equal to 14 minus 2, 2x is equal to 12, 2x is equal to 12 means x is equal to 6. So chromium is in plus 6 oxidation state. What is the electronic configuration of chromium in the plus 6 state? Chromium will have electronic configuration of argon 4s1 3d5. Chromium in the plus 6 state will have electronic configuration of argon. All the 4s1 and 3d5, all of them are removed. 4s0, 3d0. So do we have any unpaired electron in the chromium plus 6 ion? For chromium in the plus 6 state, we do not have a single unpaired electron. If we do not have a single unpaired electron, is the DD transition possible? DD transitions are not possible. If DD transitions are not possible, they should not be showing any color. But in reality, they are colored. Dichromates are orange in color. Why? Why? Because not only this DD transition, there is a next concept called as charge transfer phenomena. The color, write down this point, very important point. Color of chromates and dichromates is due to charge transfer from ligand to metal. Which is the metal? Chromium. Which is the ligand? Oxygen. So charge is transferring from oxygen to chromium. How we can say charge transfer happening? Sir, you are saying charge transfer, but how that charge transfer can happen? It is only possible with the transfer of electrons. Yes or no? The electrons are negatively charged species, so they were actually donated from the oxygen to the metal. Because of that only we are having the possibility of charge transfer. Because of this charge transfer only we are getting the metal electron. Because of that only it is showing color. All of you note down these points. The color what we see is not the color which has been absorbed by the electron. The color what we are seeing is the left out radiation color. That is the first point. And the second point is the color is responsible for DD transitions. Obviously, DD transitions are not possible whenever you have D0 configuration or D10 configuration. D0 and D10 configurations, there is no possibility of DD transitions. If there is no possibility of DD transition, there should not be any color logically. But still, chromates and dichromates, similarly permanganate, they are all colored in nature. Why? Because the charge transfer is happening from the ligand to the metal. From the ligand to the metal. Is that clear, students?
Sir,
Yes, please.
sir, in the chromates, which is the ligand?
Oxygen.
Oh, okay.
Okay. In the dichromates or chromate, oxygen is donating the electrons to the chromium. Oxygen is the ligand.
Yes, sir.
Okay. Okay, fine. Let us proceed. And we have produced dichromate from chromate. How we produce chromate? From the chromator. From the chromator, FeCr2O4, upon treatment with Na2CO3 in the presence of oxygen, I form chromate Na2CrO4. From the Na2CrO4, we have produced Na2Cr2O7 in the presence of acid medium. Now the sodium dichromate is more soluble than potassium dichromate. Sodium dichromate is more soluble than potassium dichromate. What do you mean by this? Solubility is going to be high when? Solubility. I'm
Hydration
saying,
energy is low. Hydration energy is more.
yeah, very good. Solubility depends upon two quantities. What are those? Solubility
Lattice
depends
energy
upon,
and hydration energy.
very good. Solubility depends upon lattice energy and hydration enthalpy. So when you look at these entities, the solubility of Na2Cr2O7, that is more when compared to potassium dichromate. The solubility is more means it is soluble in that water. What do you mean by that? That means you cannot have those crystals. The latter means potassium dichromate is therefore prepared by treating the solution of sodium dichromate with the potassium chloride. When you treat Na2Cr2O7 with KCl, you are getting K2Cr2O7, which is less soluble. Because it is less soluble, it will not be dissolved. If it is not dissolved, you can get those crystals. You can get the crystals. Orange crystals of potassium dichromate crystallize out. That's what they are meaning. Orange crystals of potassium dichromate crystallize out. The chromate and dichromate, as I have told you in the previous slides, they are interconvertible in aqueous solution, depending upon the pH of the solution. The mechanistic approach is not required here also. The chromate and dichromate are interconvertible in aqueous solution, depending upon the pH of the solution. The oxidation state of chromium in a chromate and dichromate is same. Like in CrO4 minus 2, what is the oxidation state? One chromium is there, 1x, 4 oxygens, 4 into minus 2. The total charge of CrO4 is minus 2. So 1 into x plus 4 into minus 2 is equal to minus 2. So x should be plus 6. In Cr2O7, 2 minus, there also we have plus 6. The oxidation state of chromium in chromate and dichromate is same, and they are interconvertible. In acid medium, the chromate converts to dichromate. In a basic medium, the dichromate will convert back to chromate. Is that clear, students? The orange crystals of potassium dichromate crystallize out. The chromate and dichromate are interconvertible in aqueous solution, depending upon pH of the solution. Look at the reactions of K2Cr2O7. It is a very strong oxidizing agent and it will be undergoing different types of ionic reactions, and the balancing of ionic reaction, one of the example, will take it and do it. The structures of chromate ion CrO4 minus and the dichromate ion Cr2O7 minus are shown below. The chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedral sharing one corner with the chromium oxygen chromium bond angle of 126 degrees. So you have the structure of chromate like this and dichromate like this. You can also say in this structure you have Cr double bond O, O minus, O minus. Okay, and dichromate is Cr double bond O, O minus, chromium oxygen chromium bond, Cr double bond O. This is also how you can understand the structures of chromate and dichromate ions. And why they have mentioned this single bonds throughout means you can have the resonating structures, negative charge coming into the pi electron and stick and move away. Negative charge can come again into pi electron and stick and move away. So you do not have these double bonds as a static bonds. They are, the pi electron and stick is not fixed there, it is delocalized. It is delocalized. That's why you have mentioned the dichromates and chromates in this manner. It is a tetrahedral structure. Chromate is tetrahedral structure. Dichromate is also tetrahedral, where the two tetrahedral units were connected by a bridged oxygen, chromium, oxygen, chromium, where the bond angle here is 126 degrees. This bond angle you can understand, you cannot have lesser bond angle than this, because at this bond angle only the repulsions between this unit and the other unit are minimum. At this angle, the repulsions between the two tetrahedral units, are less. Is that clear, students? Yes or no?
Yes, sir.
Yes.
Yes, sir.
Yes, very good. So these are the structures of chromate and dichromate is an oxidizing agent. It is a very strong oxidizing agent and it can oxidize I minus. So if you look at the reactions, acidified potassium dichromate will oxidize iodides to iodine, tin plus 2 to tin plus 4, iron 2 to iron 3, and the half reactions you can note down like this. And why it is a stronger oxidizing agent? Can K2Cr2O7, can it act as a reducing agent? Chromium is already in its highest possible oxidation stage. So if it cannot increase its oxidation state further, that means it cannot increase its oxidation state, means it cannot lose its electrons further. That means it will not lose its electrons. What do you mean by that? It will not lose its electrons. It will not undergo oxidation further. It will not undergo oxidation further means it will not be acting as a reducing agent. It can undergo reduction. That means it can act as a oxidizing agent. Oxidizing agent undergoes reduction. Reducing agent undergoes oxidation. Now try to balance one of the equation. Cr2O7 minus 2 is converting into Cr plus 3. This is one equation. And the other equation is Fe plus 2 converting into Fe plus 3. These are two half reactions. The oxidation state of chromium in Cr2O7 minus 2 is plus 6. The oxidation state of chromium in Cr plus 3 is plus 3. And we are doing this conversion, or we are doing this balancing in the presence of acid medium. Why? Because in acid medium only we have Cr2O7 2 minus in major quantity. If it is a basic medium, we preferably have CrO4 2 minus. Chromate will be there. Now look at the change in the oxidation states. Plus 6 to plus 3, decrease happened. Yes or no? So decrease in the oxidation states. What do you mean by that? Oxidation or reduction? It undergone reduction, right? Fe plus 2 to Fe plus 3, plus 2 to plus 3, increase in the oxidation states. What is it called as? Oxidation. So you have to balance these half reaction separately. How to balance this half reaction? First, balance all atoms other than oxygen and hydrogen. So here Fe plus 2, Fe plus 3, only iron is there and one iron is there. So already balanced. But if you look at Cr2O7 minus 2 to Cr plus 3, one chromium on the right hand side, two chromiums on the left hand side. To balance chromiums, what I'll do? Cr2O7 minus 2 converts to 2 Cr plus 3. First, balance the chromiums, that is all atoms other than oxygen and hydrogen. Here already they are balanced, so you can simply write the same equation again. Yes or no? So now after balancing chromium, you have oxygens left out. To balance oxygens in acid medium, this is preferably done in acid medium. In the acid medium, to balance oxygens, what you will do? To balance hydrogens in acid medium, add H plus ions. To balance oxygens in acid medium, add H2O molecules. Acid medium. In acid medium, to balance hydrogens, add required number of H plus ion. To balance oxygens, add required number of H2O molecules. We have 7 oxygens here, no oxygens on the other side. So Cr2O7 minus 2 converts to 2 Cr plus 3 plus 7 H2O. Why I have added 7 H2O? Because to balance the number of oxygens. Because of addition of 7 H2O, the oxygens were balanced. Now look at hydrogens. Because of balancing oxygens, I have 14 H plus 14 hydrogens on the product side, but no hydrogens on the reactant side. To balance hydrogens, I can add H plus ions. So Cr2O7 minus 2 plus 14 H plus gives 2 Cr plus 3 plus 7 H2O. So chromiums are balanced, 2 chromium, 2 chromium. Oxygens, 7 oxygen, 7 oxygen balanced. Hydrogens, 14 hydrogens, 14 hydrogens balanced. Only thing which has to be balanced further is charge. Because in a reaction, along with all types of atoms, charge should also be balanced. Look at this Cr2O7 minus 2, students. It has a total charge of minus 2. 14 H plus, total charge of plus 14. Minus 2 plus 14 is plus 12. What about the other side? 2 Cr plus 3. 2 into plus 3, that is plus 6. So one side I have plus 12, other side I have plus 6. What I am going to do now? I have to add electrons. How many electrons on which sides? I have to add how many electrons and on which sides? To balance a charge, add required number of electrons. If you look at this left hand side, I have 12 units of charge. On the right hand side, I have 6 units of charge. If I am adding electron, 1 electron added means I am adding minus 1 unit. So if I add 6 electrons to the left hand side, this plus 2 and 6 more electrons corresponds to minus 6. Plus 2 minus 6 corresponds to plus 6. Charge will be neutral. So what I am going to do is I will be adding 6 electrons on this side. Use 2 Cr plus 3 plus 7 H2O. This is your balanced half reaction. What about Fe? Fe plus 2 converting into Fe plus 3. Only iron is there, that is also balanced. Only thing unbalanced here is charge. To balance charge, I need to add electron. How many? 1 electron only on the right hand side, because plus 3 minus 1, that becomes plus 2, and Fe plus 2 also has plus 2. Now we have to combine these two equations. How to combine? In the final equation, I should not have any electrons. So if I should not have any electrons, I can multiply this with equation. I can multiply this equation with 6. Yes or no? So 6 Fe plus 2 converting into 6 Fe plus 3 plus 6 electrons. And now I add these two equations. 6 electron gets cancelled out. Cr2O7 minus 2 plus 14H plus 6 Fe plus 2 converts to 2 Cr plus 3 plus 7 H2O plus 6 Fe plus 3. This is your balanced equation or not? Are you understanding the students? This is your complete. Yeah, Vaidehi, any doubt?
No, sir.
All right. So this is the complete balanced equation of your balanced ionic equation of your dichromate oxidizing Fe plus 2 to Fe plus 3. Fe plus 2 to Fe plus 3 means it has been oxidized. The dichromate has oxidized Fe plus 2. That means it has been made the Fe plus 2 to increase its oxidation number. Right? These equations are very important even in your electrochemistry. Why I am saying this? Because if you look at this balanced half reaction, what is your balanced half reaction of your dichromate with Cr plus 3? Cr2O7 minus 2 plus 14H plus 6 electron is giving 2 Cr plus 3 plus 7 H2O. From this balanced equation, can I write the equivalency condition like 1 mole of Cr2O7 minus 2 is equivalent to 6 moles of electrons? Can I write like this?
Yes, sir.
So can you say what is the charge possessed by 1 mole of electrons? What is the charge contained by 1 mole of electrons?
1.6 into 10 raised to power minus 19 into Na.
So how much that would be?
96500.
96,500
1
coulomb.
Faraday. 1 Faraday.
Yeah, 1 Faraday, 96,500 coulomb. So 1 mole of Cr2O7 minus 2 is equivalent to 6 moles of electron. 1 mole of electron possesses 1 Faraday. 6 moles of electron possess 6 Faraday. So that means when I pass a 6 Faraday of electric current, I am getting 1 mole of Cr2O7 minus 2. Okay, from the electrochemistry also we can relate, like the questions can be related of your dichromates with the quantity of electric current passed through a solution and then how much quantity of dichromate is obtained. All such calculations also we can do. Right, students, these are the reactions, some reactions where Cr2O7 minus 2 is used as an oxidizing agent. Let us proceed further. Effect of heating. Write down this, very, very important. Cr2O7, K2Cr2O7, upon heating, it produces K2CrO4 and Cr2O3 and O2. 3/2 O2. Whenever you are heating the dichromate, you will be getting chromate and oxides of chromium, Cr2O3, and you will be getting oxygen also released. This is the effect of heating of dichromate. Mechanism is not required as far as inorganic chemistry is concerned. And in analysis, K2Cr2O7 is used instead of Nr2Cr2O7 because Nr2Cr2O7 is hygroscopic. Why it is hygroscopic? Hygroscopic means what? What do you mean by hygroscopic?
Water absorbing.
Water absorbing, very good. Water absorbing. Why it is absorbing water? Na2Cr2O7? Because it has
Due to its low hydration enthalpy and complex formation tendency.
So can we say it is more soluble in simple words?
Yes, sir.
Yes,
Okay.
sir.
So Na2Cr2O7 is more soluble. That is why it is absorbing the water easily. So because it is more soluble than K2Cr2O7, so whenever you're doing any analysis like quantitative analysis, titrations, it is preferably used by K2Cr2O7 because if it absorbs moisture, there can be change in the volumes. If the volumes are changed, the whole perspective of volumetric analysis is different. Right? So this is your effect of potassium dichromate, heating effect, and in the analysis we only use K2Cr2O7 instead of Na2Cr2O7. Very good. It is also used for the chloride ion test. So chromyl chloride test. So test for ionic chlorides. It is a confirmatory test. Confirmatory test. Confirmatory test to detect the Cl minus ions or chloride ions. What is this test? And what you are going to see ultimately is, I have a salt which has chloride ion. They have directly considered NaCl. Why? Because in NaCl I have chloride ion. That salt, you can just, this is a salt. Salt which contains chloride ion is treated with K2Cr2O7 in the presence of acid medium like H2SO4. You are getting CrO2Cl2 which is having a reddish orange vapors. This CrO2Cl2, these are nothing but your reddish orange vapors. When these CrO2Cl2 are treated further with NaOH, you are going to generate Na2CrO4. Na2CrO4 has what type of ions? 2Na plus and CrO4 2 minus. Nothing but chromate ions. Chromate ions are yellow in color. Chromate ions are yellowish in color. These chromate ions, whenever they are reacted with lead acetate, they will form lead chromate. PbCrO4 is formed. Why it is formed? Why PbCrO4 is formed? Because Na2CrO4, whenever it is added with CH3 C double bond O minus connected with the Pb plus 2, O minus C double bond of CH3. This is a lead acetate. So here you have Na plus and 2Na plus and CrO4 minus. These Na plus ions will preferably develop electrostatic attractions with the acetate ions to form sodium acetate. CH3 C double bond O minus Na plus is formed. What is happening whenever you have Na2CrO4 sodium chromate added to lead acetate? The attractions are developed between Na plus and acetate ions to form sodium acetate CH3 C double bond O minus Na plus. Of course, two acetates are there, so two such species are formed, and the Pb plus 2 will now form new attractions with CrO4. So PbCrO4 is formed, which is an yellow PPT. Okay, this whole thing is proceeding to CrO2Cl2, chromyl chlorides, and that is why the name chromyl chloride test. So whenever you have a salt which contains chloride ions, that salt upon treating with K2Cr2O7 in the acid medium, it will convert to CrO2Cl2, which are reddish orange vapors. You treat that with NaOH, you are getting Na2CrO4, which is an yellowish solution. You treat that yellowish solution with lead acetate, you are getting lead chromate. This lead chromate is yellow PPT. Why this reaction is important? Because the yellow solution is converted to yellow PPT. The PPT we can remove. The filtration can be done. And can I add all these reactions directly at first? Like NaCl, salt solution I have, K2Cr2O7, concentrate H2SO4, NaOH, lead acetate. Can I add all at once? If I add all at once, what will preferably happen? What will preferably happen is, we have concentrated H2SO4 and NaOH, right? Strong acid, strong base reaction will happen. Instead of converting into CrO2Cl2, you can have a reaction between H2SO4 and NaOH, which is not making the formation of CrO2Cl2 greatly. That is why you should do this reaction step by step. We have to perform chromyl chloride test. In stepwise manner. If not, H2SO4 will react, because strong acid will react with strong base and it will form Na2SO4. H2SO4 is a strong acid or a weak acid? H2SO4. H2SO4 is a strong acid or a weak acid?
Strong acid.
Why? How can you say that H2SO4 is a strong acid?
Dissociates completely.
Yeah, that's what why I'm asking. because a acid which is
Easily
undergoing,
dissociates.
yeah, that's what students. H2SO4, if it is easily dissociating to produce H plus ions, we can comment that as strong acid. But the question now here is why it is a strong acid. That means why it is dissociating easily. If you look at the structure of H2SO4, what do we have? We have S double bond O.
Due to resonance.
Conjugate base is stabilized by resonance.
Yeah, very good. Conjugate base stability, we have to look at any acid, whether the acid is a strong acid or a weak acid. We have to comment that based on the stability of conjugate base. H2SO4 has two equilibria. H2SO4 in the first equilibria it dissociates to give H plus and HSO4 minus. In the second equilibria, hydrogen sulfate ion that will dissociate again to give H plus and SO4 2 minus ions. So what you will be generating? H2SO4 will be giving 2H plus and SO4 2 minus ions. So this is your acid. H2SO4 is acid means SO4 2 minus is a conjugate base, Cb. So if it dissociates, 2H plus ions are lost and we get S double bond O, S double bond O, O minus, O minus. So the sulfate ion will be resonance stabilized. SO4 2 minus is, it is resonance stabilized, and thus H2SO4 is strong acid. What about acetic acid? Acetic acid is strong acid or not?
No.
Why? Acetic acid is giving acetate ion and H plus ion. Acetate ion is also having resonance. And if you look at acetate ion,
complete dissociation does not take place.
yeah, that's what students, very complete dissociation happens. If we say strong acid, complete dissociation occurs. If we say weak acid, complete dissociation will not occur. The question I am asking is, why complete dissociation occurs? Why complete dissociation do not occur? Okay, the question is that's what only. What is the question? Acetate ion is a weak acid means why it is not undergoing complete dissociation. If you look at acetic acid, it has CH3 C double bond OH. It can dissociate to give CH3 C double bond O minus and H plus. Yes or no? In the acetate ion also we have resonating structure. This negative charge can come into this pi electron density can move away. We can have CH3 CO minus C double bond O. We do have resonating structures in acetic acid or not? Yes or no? We do have resonating structures in acetic acid, but if you look carefully, the acetic acid is connected, the C double bond O minus is connected to alkyl group. What is this alkyl group? Electron donating group or electron withdrawing group?
Electron donating group.
Electron donating group. We have the resonance hybrid like this. And this alkyl group is electron donating group. In the C double bond O minus, already we have extra negative charge, and the CH3 is donating the electrons, making it unstable or more stable. Electronic repulsions are, yes, electronic repulsions are high, making it unstable. But SO4 2 minus is more stable. Since this is slightly unstable, you are getting less dissociation happening. That is why acetic acid is a weaker acid when compared to H2SO4. Can you compare the acidic nature of acetic acid with phenol, which is strong acid, and why? Acetic acid and phenol, all are interlinking questions, students. We are talking about the reactions of
Yes, sir.
H2SO4. Yes, Faizan?
Sir, I think phenol is more acidic because of its it has more resonating structure than acetic acid.
Okay. Anyone else? Yeah, what Faizan says is the general idea which students will get. If you look at acetic acid, CH3 C double bond OH, you have CH3 C double bond O minus plus H plus. If you try to write the resonating structure, you will get CH3 C O minus C double bond O, negative charge coming into pi electron density moving away. These are the resonating structures in acetic acid. Phenol, you write down. Phenol PHOH, it will convert to phenoxide ion and H plus ion. This phenoxide ion has resonating structures. How? The negative charge on oxygen can come into pi electron and still moves away. You have C double bond O, negative charge at the ortho position now. Negative charge again come into pi electron and stick and again move away. We have double bond O, O minus. Negative charge can come into pi electron and stick and move away. Negative charge here, double bond O. Negative charge can come into pi electron and stick and move away. We have double bond O minus. How many resonating structures are there here? 5 resonating structures. How many are there here in acetate? 2 resonating structures. Greater the number of resonating structures, greater should be the stability or lesser should be stability?
Stability.
Stability should be high. So which should be having high number of resonating structures? Phenol. That is phenoxide. So phenoxide should be more stable if you think according to number of resonating structures. But in reality, acetate is more stable. Why? Because in acetate, whatever the 2 resonating structures we have drawn, they are equivalent resonating structures or not? CH3 C double bond O minus, CH3 C double bond O minus, 2 structures, 2 resonating structures, both are equivalent. Both are equivalent. If you look at the resonating structures of phenoxide, are they equivalent, all of them? Negative charge on the first structure is an oxygen, second structure on carbon, third structure on carbon, fourth on carbon, fifth again on oxygen. Are they equivalent, Farhan?
No, sir.
No, right? So the 5 resonating structures in phenol are non-equivalent. The 2 resonating structures in acetate are equivalent. Also, in acetate, where is the negative charge in the resonating structures? Negative
On
charge is present
oxygen.
on oxygen,
And
which is more
carbon.
electronegative.
Yes, sir.
In the resonating structures of acetate, more negative charge is present on more electronegative oxygen atom, whereas in phenoxide, the negative charge is present on carbon in 3 of its resonating structures. Because of all these reasons, phenoxide is less stable when compared to acetate. So therefore, acetic acid CH3CO minus is more stable than PHO minus, and thus CH3COOH is a stronger acid. Understood now, all of you? These are all the interlinking questions. Understood, Vaidehi? Good. So let me now ask again question regarding the acidic natures. HCl and DCl, which is acidic? HCl and DCl. HCl is hydrogen chloride, DCl is deuterium chloride. What is deuterium?
Isotope of hydrogen.
Yeah, which is stronger, which is more acidic now? I am calling the acidic nature of DCl by giving D plus ions. HCl gives H plus and Cl minus. DCl gives D plus and Cl minus. You compare, like in HCl, we are comparing the more number of H plus ions obtained as more acidic, right? In the DCl, you compare more number of D plus ions are more acidic. Which should be generally more acidic, HCl or DCl?
So DCl.
Prachi says DCl. Why? Reasons are important.
Sir, HCl.
Yeah,
Sir,
HCl.
I think HCl.
Yeah, that's what I'm asking students. Reasons are important. Why?
Bond will
Sir-
easily break, so release of hydrogen ion will be easy in HCl.
So if you look at HCl and DCl, the hydrogen also has 1 electron, deuterium also has 1 electron. The only difference is between HCl and DCl. What is the only difference?
It has one neutron. DCl has 1 neutron and a proton.
Yeah. What about hydrogen? Hydrogen has.
Doesn't have proton. Oh, sorry,
So what is
neutron.
this new? Yeah. What is this neutron doing now? Neutron, is it involving in the reaction?
No,
No, it is inside the nucleus. So will it affect the acidic nature, or can I say both are equally acidic?
sir, we can say both are equally acidic because neutron isn't taking place.
but still, although neutral is not having any role in the reaction, it has a role in the mass because deuterium is more heavy when compared to hydrogen. Now you may ask a question, sir, what is that mass doing? If you think carefully, we'll understand this reaction. Listen carefully. HCl and DCl, only one difference is there. What is that? Mass. I think you might have remembered about Bohr's theory. What is the first postulate or the equations of Bohr's theory? 1 by 4
MVR is
pi.
equals to NH upon 2 pi.
Yeah, MVR is equals to NH upon 2 pi.
NH by
And
2
other
pi.
equation is 1 by 4 pi epsilon naught Q1 Q2 by
Q1 Q2 by R square.
R square is equals to MV square by
MV
R.
square by R.
You try to solve these two equations for radius. Can I say velocity V is equals to NH by 2 pi mr? And substitute that velocity here? For sure, no? So if I substitute the velocity here, what I'm getting is 1 by 4 pi epsilon naught Q1 Q2 by R square is equals to M by R into V square. What is V square? N square H square by 4 pi square M square R square. R square got cancelled out. So what is our expression for radius R? R is equals to M N square H square divided by 4 pi square M square. Here you have 4 pi epsilon naught and here you will be having Q1 Q2. Mass is going to be cancelled out one times. So radius is equals to N square H square 4 pi epsilon naught divided by 4 pi square Q1 Q2 into 1 by M. Yes or no? N square H square 4 pi square epsilon naught 4 Q1 Q2 4 pi square Q1 Q2, all these are same because hydrogen, deuterium, they are all one electron species. Yes or no? So all this is constant. So radius of the orbit in which the electron is revolving, that is actually inversely proportional to mass or not. What is that mass? Mass is for the mass of electron or mass of neutron or mass of nucleus. What is this M stands here? Mass of
atom.
Mass of atom or mass of electron?
Atom.
Around the nucleus, electron is revolving. No.
Electron.
Yes or no? So mass of electron. That means the radius of an orbit in which the electron is revolving, that is inversely proportional to mass of electron. This is true when the electron is only revolving around the nucleus and nucleus is static. But in reality, nucleus also has some motion. In reality, nucleus is not static, it is also having some motion. So can I simply say mass of electron, or I have to replace this mass of electron with reduced mass of electron? How many of you have remembered concepts of reduced mass from your physics? Whenever I have two particles of different masses m1 and m2 moving, I can replace these two particles with a single particle of mass reduced mass. Now
M1
not
M2
only
upon M1 plus M2.
very good, reduced mass of electron nucleus will be mass of electron into mass of nucleus by mass of electron plus mass of nucleus. So which will have greater reduced mass, deuterium or hydrogen? Deuterium and hydrogen, if you look at, deuterium will have more mass because it has neutron. So radius of the orbit in which the electron is revolving, that is inversely proportional to mass of electron earlier. This is a scenario, but I have replaced mass of electron with reduced mass. Why? Because the nucleus is also not static, it is also moving. So radius is actually inversely proportional to reduced mass. So which has more reduced mass? Reduced mass of deuterium is greater when compared to hydrogen. So if reduced mass of deuterium is greater, what should be the radius? Radius of the electron, radius of the orbit in which the electron is revolving in deuterium, that is less when compared to hydrogen. That means if you look at HCl and DCl, the electron density here in the hydrogen, since the radius of the electron in the case of hydrogen is more, so it will be moving in a greater radii. If you look at DCl, the electron is moving in a smaller radii. So if electron density is moving in a smaller radii, can I say DCl bond is stronger bond? because overlapping would be great. In the DCl,
Yes,
the
sir.
electron density is moving in a smaller radii. Smaller radius means small size. Small size means great overlapping. So in DCl, overlapping is strong. If the overlapping is strong, can I say bond energy is high? DCl is stronger bond, has more bond strength, bond energy. HCl has less bond energy. Less bond energy means easily broken or not. So which bond is weaker? HCl bond is weaker. If HCl bond is weaker, that bond can be easily broken. So HCl can give out H plus ions easily when compared to DCl, giving the D plus ions. These are just the interlinking concepts, students. You don't panic. I'm just giving you all the idea of how the questions can be asked, how the questions can be interlinked. Okay, you don't
Sir,
need to panic. Yes, yes, please.
sir, could you explain the overlapping and the bond energy part?
So radius smaller. Like I have two atoms. So electron density in one atom is like this. Other atom is like this. These two are overlapping now. If they overlap, you have, this is a scenario. This is the overlapping bond. Every bond is due to overlapping, right?
Yes, sir.
Okay. These two electron density overlap. This is the overlapping scene. And we have two another electron densities like this, which are overlapping now. Where the overlapping is great. Size larger means overlapping is less. Size smaller means overlapping is great. Large size atoms or electron density present in a large size that cannot overlap greatly or effectively. So if you look at DCl, in that we have seen the deuterium has a lesser radius. That means electron density in deuterium is moving in a lesser radii. That means it will have more overlapping or not. Lesser radius
Yes,
means
sir.
smaller. Smaller means overlapping is greater. Overlapping greater means what? Stronger is the bond. Greater the overlapping, greater the bond energy. So DCl is a stronger bond. So DCl is a stronger bond. That means that bond cannot be broken easily. HCl is a weaker bond. That means that can be broken easily. So which is more acidic now?
HCl.
HCl. So that's what. Like that, we can interlink different types of questions with your D block as well. Right, students? K2Cr2O7 on reaction with H2O2 produces a blue color solution forming CrO5. CrO5 formation we'll understand now. Yeah, this was the reaction. Write down all of you. K2Cr2O7 will be converted to CrO5 whenever you treat this K2Cr2O7 with H2O2. Of course, in the acid medium. If you do not have acid medium, the dichromate will convert to chromate. The CrO5 has butterfly structure. This is the structure of CrO5, butterfly structure. And what is the oxidation state of chromium in CrO5? Oxidation state of chromium in CrO5. K2Cr2O7 in the presence of acid medium. Yes, someone said +6. That is +6, very good. Because if you look at a CrO5 butterfly structure, one oxygen is doubly bonded with chromium, which has an oxygen state of -2. Remaining all four oxygens are involved in the peroxy bonds. For peroxy bonds, the oxygen state is -1. So -1, -1, -1, -1. Chromium is bonded with all the four oxygens, -2, -1, -1, -1, -1. So chromium should be in the +6 stage. So you cannot directly say, can I directly say one chromium is there, so 1 into x, 5 oxygens are there, 5 into -2, that is equals to 0. So x is equal to +10. Can I directly say like this? If I directly apply the formula, I'm getting the oxidation state of chromium is +10. But if you look at the structure, the oxidation state of chromium is +6. And we all know +6 is the correct structure. +6 is the correct one. Why this is wrong? Why it is wrong means here we have automatically considered that all the 5 oxygens were having the oxidation state of -2. But from the structure, there are 4 oxygens which are involved in the peroxy bonds. Oxygen, general oxidation state is general oxidation state is -2. In peroxy bonds, in peroxy acids, it has -1 state, -1 oxidation state. K2Cr2O7 upon treatment with the hydrogen peroxides in the acid medium produces CrO5. And this CrO5 upon treatment with the pyridine, it can form a complex like CrO5 dot pyridine, which is blue in color. And it can also be converted to Cr plus 3 if you expose that to heat, which is actually green in color. This is about the reactions of K2Cr2O7 to CrO5. Is that clear, students? Whatever discussion we have made till now, is that clear or not?
Yes, sir.
Clear? Very good. Then comes the next important compound like potassium permanganate, KMnO4. It has similar preparations like similar reasons, whatever I have told you in the K2Cr2O7, the similar reasons I can say here. It is also colored. Potassium permanganate is prepared by fusion of MnO2 pyrolysites with an alkaline metal hydroxides, and it acts as an oxidizing agent. KMnO4 also acts as an oxidizing agent, but in the preparation, the oxidizing agent like KNO3 is used. Write down these preparations. This D block element, D block and F block, mostly about remembering. You have to remember all these things carefully. MnO2 plus KOH plus O2, that will form K2MnO4. K2MnO4 means what? You have 2K plus and MnO4 2 minus ion. Yes or no? This MnO4 2 minus is again reacting in the acid medium. It will form MnO4 minus. Write down these reactions. The potassium permanganate is prepared by the fusion of MnO2 pyrolysites with an alkaline metal hydroxides and an oxidizing agent like KNO3. This MnO2 is converting into K2MnO4. That K2MnO4 in the acid medium, it converts to MnO4 minus and MnO2 back. This is nothing but your permanganate ion. It is already in. It is already in +6 oxidation state. +7, not +6, +7 oxidation states. And thus acts as oxidizing agent. MnO4 minus, it is a strong oxidizing agent. Strong oxidizing agent. Right? Is that clear, Suman?
Yes, sir.
Yes. Write down the preparation method. All of you write down the chart. MnO2 plus K2CO3 or KOH. We are getting K2MnO4 manganate from the K2MnO4, which is actually green in color. We are getting permanganate KMnO4. This K2MnO4 is converted to permanganate. K2MnO4 green in strong basic medium is stable. It is K2MnO4 is stable in basic medium, but in acidic medium it disproportionates. In acidic medium it will disproportionate. K2MnO4 will have MnO4 2 minus. It is converting into MnO4 minus plus MnO2. What do you mean with this? The +6 oxidation state is changing to +7 and a +4. So it is undergoing the increase in the oxidation state as well as decrease in the oxidation state. The same element from the same compound undergoes oxidation and reduction. Same element from the same compound, if it undergoes oxidation and reduction, it is nothing but disproportionation. The K2MnO4 is stable only in the strong basic medium. In acidic medium, it will disproportionate to MnO4 minus and MnO2. So K2MnO4 in the acid medium, it forms MnO4 minus and MnO2. If you do the electric oxidation, industrial method also, in the presence of electrical energy also, you can convert the K2MnO4 to KMnO4. And K2MnO4 you can treat with O3 and form KMnO4 and O2. You can treat this with O3 as well, ozone. The mechanisms for inorganic reactions were not required, as I am repeatedly saying. K2MnO4 treated with Cl2, it will also form KMnO4 and KCl. So these are the different ways to convert K2MnO4 manganetes to permanganates KMnO4 by electric oxidation, by treatment with an acid, or by treating with O3 or with a chlorine Can I proceed further, students?
Yes, sir.
Yes, very good. In the laboratory, manganese 2 ion is oxidized by peroxide disulfate to permanganate. In the laboratory way, if you want to prepare permanganate ion, we have to convert the S2OA2 minus, that is peroxide disulfate. This will be converting into your SO42 minus sulfate. This is peroxo disulfate. In the P block, like in the group 16, you are going to write the structures of all the oxy acids of sulfur. There we look at how the structure of peroxide disulfate will be, how many S double bonds are there, how many SO bonds are there. But what we can say here is the peroxide disulfate can be converted to sulfate, and along with that it is converting the Mn+2 to MnO4 minus. The manganese from the +2 state went to the +5 state. That means it has been undergone oxidation. So which is oxidizing Mn+2? The peroxide disulfate. So peroxide disulfate oxidized Mn+2 and converted that Mn+2 to MnO4 minus, which is permanganate. And it is purple colored. Again, why it is showing color? Color is due to charge transfer phenomena. Due to charge transfer phenomena from oxygen to manganese or ligand to metal. Capital L stands for ligand, capital M stands for metal. It is an oxidizing and itself, it is an oxidizing agent and itself gets reduced into Mn+2 and acts as an autocatalyst. This MnO4 minus will act as an autocatalyst. Autocatalyst means what? Autocatalyst means what? Means it will catalyze. Autocatalyst means it will catalyze its own reaction. Its own reaction. Yes or no? Yesterday we have discussed about catalysts. We have discussed about positive catalyst, negative catalyst. Positive catalyst increases the rate of the reaction. Negative catalyst decreases the rate of the reaction. We have seen why it will increase, why it will decrease. The positive catalyst increases the rate of the reaction by decreasing the activation energy. The negative catalyst decreases the rate of the reaction by increasing the activation energy. Autocatalyst means once the species is formed, then it will be catalyzing the reaction. So it will catalyze its own reaction, and as it is formed in the reaction, the rate of the reaction increases. Initially, rate of the reaction will be slow, but as it is formed in the reaction, the rate of the reaction will be increased. Okay, it is an oxidizing agent and itself gets reduced to Mn+2, and it acts as an autocatalyst. It will be acting as an autocatalyst. Since it is an oxidizing agent, we can also have similar reactions of Cr2O7-2. Is that clear, students? Can I proceed further?
Yes, sir.
Yes, sir.
Yes, very good. Okay. If you look at physical properties, MnO4 minus and MnO4 2 minus. Write down this, all of you. The manganate ion and permanganate ions are tetrahedral. Of course, MnO4 2 minus, MnO4 minus, both are tetrahedral in nature. Like manganese is connected to oxygens, double bond O, O minus, O minus. This is your MnO4 2 minus. MnO4 minus is Mn double bond O, O minus. The manganate and permanganate are tetrahedral. The pi bonding takes place by overlapping of p orbitals of oxygen with the d orbitals of manganese. Manganese is a d block element. The d orbitals of manganese overlap with the p orbitals of oxygen. Oxygen electronic configuration is 1s2, 2s2, 2px2, 2py1, 2pz1. You have p orbitals of oxygen like 2py1, 2pz1 has only one electron. In the manganese also, you have argon 4s and 3d. Yes or no? Argon 4s and 3d. The p orbitals of oxygen overlap with the d orbitals of manganese. So what type of bond is this? A p pi d pi bond. The manganese forming a double bond with oxygen, which is a p pi d pi bond, and manganate is green in color. Like MnO4 2 minus is green in color. What about MnO4 minus permanganate? What is the color of permanganate?
Purple.
Purple in color. Very good. Permanganate is purple in color, and both are colored because of their charge transfer phenomena only. The green manganate is paramagnetic. Why it is paramagnetic? Because of one unpaired electron. Because in manganate, if we have manganese in which stage? MnO4 2 minus. One manganese 1 into X, 4 oxygens 4 into minus 2. That is equals to minus 2. X should be equal to plus 6. So if you write the electronic configuration, manganese in the plus 6 state, it will have argon 4s0 3d1. So it has one unpaired electron. Because of that one unpaired electron, it is going to be paramagnetic in nature. If it is paramagnetic, it will be weakly attracted by the external magnetic field. But permanganate is in manganese in plus 7 stage, where you have argon 4s0 3d0. There is no unpaired d electron. Because of the absence of unpaired electron, permanganate is diamagnetic. That means permanganate is weakly repelled by the external magnetic field. Understood this point, students? Clear or not?
Yes, sir.
Yes, very good. And we have the oxidizing property as well. We will discuss about the oxidizing properties in the next class, and along with that, the F block elements will complete. So I am actually discussing a lot more things which are slightly difficult to understand also. Okay, because the bond energy cleavages, which is going to be strong bond, but don't panic. If you prepare for the difficulty level only, you will be understanding the basic concepts easily. Don't need to worry at all. Just try to learn as much as possible. Okay. All the best. Thank you all. Bye-bye.
Thank you, sir.
Thank you.
Thank
Thank you, sir.